Hi everyone. Today let's talk about section 4.2, what derivatives tell us. Big idea. Derivatives can be used to compute properties of the graph of a function. The derivative of a function is positive on the intervals where the function is increasing and is negative on the interval where the function is decreasing. The sign of the derivative is different on either side of an extremum. Okay, big skills, you should be able to prove that a critical point is an extremum by showing that the derivative has opposite sign on each side of the critical point. Okay, so let's look at definition. A function is increasing on an interval if f of x1 less than f of x2 whenever x1 less than x2. So if I want to draw a picture, okay, let me choose, how about green? Okay, so this is the picture. We have x1 and x2 right here. This is f of x1. This is like f of x2. So you can see f of x2 is greater than f of x1. Okay, so the function is increasing. Okay, and then the function is called decreasing if f of x1 is greater than f of x2. So we still have x1 less than x2, but f of x1 is greater than f of x2. So that's why we have a decreasing function. Okay, so let's look at this picture. So you can see here, the function is increasing from point A to point B, and it's decreasing from B to C, and then it's increasing from C to D. Okay? So if the function is going up, then it's increasing. If the function is going down, then it's decreasing. Okay? And furthermore, when the function is increasing, what is special about the slope of the tangent line? Let's look at this. So here, oops, let's see, okay, so here you can see the tangent line, the slope is actually positive. Okay, how about at B? What's special? Well, at B the slope is 0, and then between B and C, what happened? The slope is actually negative. So that's why when the function is increasing, we will get the slope is positive. Okay? And if a function is decreasing, we will have the slope is negative. And you can see at point P, the slope at point P, we actually get a local maximum. Okay, so we have a local maximum here. Our slope is 0. And point C, you can see we have a local minimum. So point B, we have a local max. And point C, we have a local min. And the slope is also 0. So the slope, do you remember last session we talked about we have maximum and minimum. That is when the derivative is, so we have critical points when the derivative is 0 or does not exist. Okay, so actually we will have we might have local mass and local mean at the critical points. Okay, so test for intervals of increase and decrease. Suppose f is continuous on an interval I and differentiable at any interior points of I. Okay, if the derivative is positive at all interior points of I, then f is increasing. Okay, so it's like that. Right, the slope is positive, is increasing. And if the derivative is negative at all interior points of I, then f is decreasing on I. So see, the slope is negative, so it's decreasing. And then we have the theorem. First, derivative test. Suppose that f is continuous on an interval that contains a critical point C. Assume that f is differentiable on an open interval containing C, except possibly at C itself. Okay, if f prime change signs from positive to negative. Positive means like going up and negative like going down, right? So the picture is like that. So if f prime change signs from positive, this is positive, to negative, okay? Then f, so this is like the c value. Then f has a local maximum. So this is local maximum at c. Okay, so f might be defined, f prime might exist at c, and maybe f is not differentiable at c. So we might have like picture like that. Okay, so f is still increasing, the slope is still positive, and here f is decreasing, the slope is negative. But here we can see f prime in this case does not exist, but this is still a local max. Okay, so this picture, f prime of c is 0. Okay, so that is this case. Okay, second case. If f prime change sign from negative to positive, okay, as x increases through c, then f has a local minimum. So change sign from negative to positive, this is like the picture. Right here, so it's negative, here slope is positive, here the slope is 0, and you can see we have a local minimum. Okay, so actually, and the picture could be something like that, and here f prime of c does not exist, but we also have a local minimum. Okay, because here the slope is negative, here the slope is positive. Okay, and if f does not change signs at c, okay, if f does not change signs at c, then f has no local extreme values at c. So this picture is like this one. Okay, you can see f is increasing here. Here f is also increasing. Here, even though the m is 0 or might not be 0. Okay. So yeah, critical point means it's either 0 or does not exist. Okay, it could be something like that. Okay, so it does not exist here. Okay, so in this case, we don't have local extreme values at c. Okay, you can see it's neither local max nor local min. Okay, so that is the third case. Okay, so this is the first derivative test. Let's look at example 1. Find where the function's f is increasing and where it is decreasing, and then also find the local extreme of f. All right. Okay. So the first step is compute the derivative. Okay. So the derivative of 12x cubed minus 12x squared minus 12x plus 12. Oh, all the coefficients are 12, so we can factor that out. And then we have what? Oh, let me see. So here we have x cubed minus x squared minus x plus 1. Right? All right, let's continue. So when we have 4 terms, how do we factor it? We usually group the 2 terms together and find the common factor. Okay, so the common factor of the first 2 terms is x squared, and we have x minus 1. And then we can factor out the negative, and then the last 2 terms, we get x minus 1. Now you can see this is the common factor. So we have 12x minus 1, x squared minus 1. Can we factor it further? Yes, because x squared minus 1 is x plus 1, x minus 1. Okay, can you see that we have two copies of x minus 1? We can combine together. So this is what we get. We set this equal to 0. All right. And we solve for x. So this factor, okay, so what are the critical points? This guy gives us x equals to 1. This guy gives us x equals to minus 1. Okay, so we have two critical points. So the second step is to find the domain. What are the domain? Well, polynomial, right? So polynomial, no restrictions, or real number. Okay, the third step, we're gonna draw a table. Okay, so let's draw the table. Because the domains are real numbers, so we draw the whole real line. And let's plot the critical points. We have minus 1 and 1. Okay, now you can see the critical points separate this real number line into 3 subintervals. So we have minus infinity to minus 1 to 1, 1 to infinity. Okay, what do we want to look at? So imagine this is like a table, and we want to consider f prime and f. Okay, so we want to consider the values of f prime and f over these intervals and the numbers, critical numbers. Okay, so f prime, we know the critical points are 1 and minus 1. It means f prime is 0 over those two numbers. Okay, and then in order to figure out f prime on this interval, so we want to plot some value from this interval. Okay, so I forgot to mention, for f, you want to fill it is either positive or negative, so we want to fill that in. For f, we want to fill in either increasing or decreasing. Okay, so that's why here we pick a point in the interval minus infinity to minus 1. What number shall we pick? Yes, minus 2. And you want to plug in f prime. Where do you plug in? Do you want to plug in which color? Okay. Do you want to plug in this formula or this formula? We want to always plug in the factored form. Okay, so here we plug in the factored form. Okay, which is this guy. Okay, so we plug in minus 2. 12 is positive. Minus 2 minus 1 is minus 3. But square, it become positive. Minus 2 plus 1 is negative 1, so it's negative. Okay, so this is negative. What number do we pick here? 0. 0 is in this interval. So when we plug in 0, 12 is positive. X minus 1 squared is always positive. And then x plus 1 is 1, also positive, so we have positive. Okay, what number do we pick over the interval 1 to infinity? Yes, we can plug in 2. Then 12 is positive. 2 minus 1 squared is positive. 2 plus 1 is 3, is also positive. Okay, so once we figure out that, we can then remember if f prime is negative, your function is increasing or decreasing. Decreasing. If f prime is positive, then our function increasing. Okay, if f prime is positive, our function increases. Okay, think about it. Now our function decrease and increase. What is this guy? Locomain, right? And if our function increase and then increase, what is this guy? Neither locomean nor locomax. Okay, so that's why we can conclude f is increasing on the interval minus 1 to 1 and 1 to infinity. F is decreasing on minus infinity to minus 1. Okay, and f has local minimum at x equals to -1, and f has no local maximum. Okay, so this is how we answer the problem. All right, let's continue and look at example 2. Find the local extrema of f. Okay, so we follow the same steps. Could you please pause the video and try to work on this problem first? Okay, are you done? Yes, let's check our answer. So f prime is, this is a product, so we use product rule. It's the derivative of the first guy times second guy plus first guy times the derivative of the second guy. Okay, so what's the derivative of the first guy? Oh, it's power rule. You copy down the exponent and x to the 2/3 minus 1 is minus 1/3. 2 minus x. All right, the derivative of 2 is 0. The derivative of minus x is minus 1. Okay, so what is that? Well, let's write it better. So the first factor, 3 is in the denominator. X to the negative 1/3, it means we can put x to the 1/3 in the denominator. And then we have 2 on top. 2 minus x is on top. Okay, when you try to simplify it, you want to make it clear what is in the denominator, what is in the numerator. And then here we can take the common denominator. Okay, so and the 2 we can distribute. We get 4 minus 2x minus x to the 2/3 times 3x to the 1/3. Wow, what is x to the 2/3 and x to the 1/3? Well, that is actually x. Okay, so that's why we have 4 minus 2x minus 3x. And that is 4 minus 5x. Okay, remember if we have a quotient, okay? So when we have a quotient, what do? Not quotient rule. We're not trying to take the second derivative. Okay, remember, in order to find critical points, if your f prime is a quotient, so by letting the numerator 0, we get f prime is 0. Okay, so numerator 4 minus 5x is 0. Okay, when do you get f prime does not exist? That corresponds to the denominator is 0, which is 3x to 1/3 is 0. So this guy we get x 4 equals to 5x. So x is 4 over 5. Here we get x is 0. Okay, so the second step, we figure out the domain. So here we get cube roots. Cube root is fine, right? Square roots, we need the things inside the square root to be positive, greater or equal to 0, but cube root is fine. So domain is all real numbers. All right, so step 3, we want to draw the table or a diagram. Okay, the real number line. Because the domain is all real numbers, you draw the real number line. But if the domain is not all real numbers, then you draw like whatever's your domain is. Okay, all right, what other points? 0 and 4/5. That separates the real number line into 3 sub-intervals. Okay, so we have f prime and f. So f prime, remember 0. 0 actually make the denominator 0, so it does not exist there. And 4/5 is actually making the numerator 0, so f prime is 0 there. Okay, and then look at each piece. Remember when we plug in, where do we want to plug in? We want to plug in the form, okay, the last form. So we want to plug in here. Okay, what value is in the interval minus infinity to 0? -1. So let's pocket it. 4 minus 5 times -1 is like 4 plus 5 is 9, so it's positive. But the denominator cube root of -1 is -1, so the answer is negative. Can you find a number in between 0 and 4/5? Maybe 1/5, right? When we plug in 1/5, 4 minus 5 times 1/5 is 1, so 4 minus 1 is 3, so positive. The denominator is also positive, so the answer is positive. Okay, can you find a number that's in the interval 4/5 to infinity? Yes, 1. So the numerator 4 minus 5 is -1. The denominator, we get positive, right? So numerator negative, denominator positive, the answer is negative. All right, so let's continue. If f prime is negative, what is f? Increasing or decreasing? Decrease. F prime positive, then f increases. F prime is negative, then f is decreasing. All right, now let's think about it. A function decrease and then increase. What is this guy? Local mean. Okay, and a function increase and then decrease. What is this guy? Local max. Okay, yeah, you can draw a picture to help you understand. Okay, so let's make a conclusion. F is increasing on 0 4/5 and is decreasing on minus infinity 0 and 4/5 infinity. Okay, F has local mean at x is 0 and local max at x equals to 4/5. Okay, all right, so that is example 2. Okay, how about example 3? Okay, please pause the video and try to work on it first. We have tons of examples. Okay, and that's good because videos I can actually record like more examples and you can read it at any time. Okay, so we don't need to worry about, oh, time's up, bye guys, like that. So yes, we can watch the video when you are free. So we don't have a standard form, so let's make it into the standard form. Okay, then we have 32, you multiply by -2, and then you have x to the -3, right? So we have 1, then we have -64. X cubed is actually in the denominator. So whenever you see a negative exponent, don't forget to put it in the denominator. Okay, common denominator. Then we get x cubed minus 64. Okay. All right, what is that? Okay, so do you know that 64 is actually 4 cubed? How can we factor this guy? You can if you can remember, a cubed minus b cubed is a minus b, a squared plus ab plus b squared. If you can remember that, okay. So this guy is x minus 4 because 64 is like 4 cubed, and then x squared plus 4x plus 16. Okay, so if you don't remember that, it's okay. In this case, you don't need to factor completely. Okay, so oh wait, how do we find critical points? Okay, you said the numerator Okay, numerator is 0. So actually this guy is, it won't be 0 because the discriminant, so this guy, the discriminant is negative, so no real solution. Okay, so no real root, if this is how we say. Okay, alright, so that's why the numerator x equals to 4, this guy equal to 0. This won't be 0. This guy is always positive, actually. So the only possible is when x minus 4 is 0. So x equals to 4. Okay, and we can have f prime does not exist. That is when the denominator is 0. So that gives us x is 0. So let's see. What is the domain? So we have fractions, so the denominator cannot be 0. Oops. So this guy actually is not a critical point. Okay. So 3, when we draw the diagram, okay, remember we draw the domain. So the domain x cannot be 0. So x cannot be 0. So you actually need to put an open circle around the 0. My open circle is not good. Okay, like that. And then we have 4. Where's 4? Oh, 4 is like here. Okay, so then you can see 4 separates the domain into like 2 pieces. Okay, so that is why here f prime and f. Okay, so at 0, this is undefined. Okay, so we don't have this value, so actually this is undefined. Yeah, it's outside of the domain. Okay, at 4, we know f prime is 0. Okay, so how about from minus infinity to 0, 0 to 4? So actually, this interval and this interval will have the same f prime. The f prime will have the same sign over this 2 interval. Okay, because f prime only change signs when you pass through 4. Okay. Oh, sorry. You also change signs when you pass through x cubed. All right. So we actually need to check carefully. Okay. Yes. All right. Okay. Let's pick a number in the interval minus infinity to 0. Let's pick minus 1. Okay. And we plug in the factor form. Okay. So let's see. We pick 1 and we plug in here. Okay, so when we plug in 1 minus 4 is minus 3. That is negative. And this quadratic term factor is always positive. Okay, why is that? You remember the quadratic factor? Okay, there are 3 possible cases. It could be like that, it could be like that, it could be like that. Here, the discriminant is b squared minus 4ac. I hope you can remember that, because that is what? 2a minus b plus or minus square root of b squared minus 4ac. The discriminant is actually the things inside the square roots. So if the discriminant is positive, we have 2 real roots. So you can see we have 2 x-intercepts. And here is when the discriminant is 0. So you only have 1 repeated real root. Repeated because your quadratic function is just gonna be a complete square. Okay. Oh, I put it wrong. I mean 0. And here is when the delta, the discriminant, is negative. Then we have no real roots. Actually, we have 2 complex roots. Okay. And then so that's why here where in the third case, the quadratic function always lie above the x-axis, so it's always positive. Okay, so where were we? We're talking -1. So -1 minus 4 is -5, negative. This factor, quadratic factor, is positive. -1 cubed is negative. So negative give us positive. Oops. Okay, and then on the interval from 0 to 4, we can plug in 1. 1 minus 4, negative. The quadratic factor, positive. 1 cubed is 1, right? Positive. Oh, negative, positive, we get negative. Okay, so we gotta be very careful. Okay, so how about on the interval from 4 to infinity? Okay, we can pick 5. 5 minus 4 is positive. 5 cubed is positive, so we have positive here. Okay, so if f prime is positive, f is, do you know what it is? Yes, increasing. If f prime is negative, then f is decreasing. If f prime is positive, then f is what is that? Increasing. Yes. So that's why here decrease and increase, what is this guy? Local mean. We have a local mean here. Okay, but this guy, we actually has neither local mean nor local mass, because our function 0 is not defined. So you kind of expect something like that, like a asymptote over there. Okay, so you can answer a problem like f is increasing on -infinity to 0 and 4 to infinity, decreasing on 0 to 4. F has local mean at x equals to 4, and f has no local maximum. Okay, all right. Example 4. Find the local extrema of f of x equals to x to the x. Okay, first step, we want to find what is f prime. Well, if you can remember, when you see x both in the base and the exponent, what do? Yes, the logarithmic differentiation. So y equals to x to the x. That's the first step, and then we apply ln on both sides. Okay, and ln of x to the x. So what happened? We can put the constant in front. So we have x, ln of x. Okay, and then we're ready to differentiate. So 1 over y prime. Here, product rule. First guy prime times second guy plus first guy times second guy prime. Okay, x prime is 1. Derivative of ln of x is 1 over x. So that's why 1 over y times y prime is, they cancel, we have ln of x plus 1. So y prime is ln of x plus 1 times y, but y is x to the x. Okay, that's f prime. We set it equal to 0. Okay, so you know the exponential term always positive, so the only possibility to make this guy 0 is when the factor ln of x plus 1 is 0, ln of x is -1 raised to the power b, so we get e and ln cancel, we have x equals to e to the -1. Okay, so this is the critical point. Okay, what is the domain? Well, the domain of this function is we have if you see the exponential function, then the base has to be positive. Okay, so that's why we have minus 0 to positive infinity. Why is that? You cannot have negative number because if you have negative number, then your exponent could be 1/2, right? Well, then you're gonna be you're gonna have square roots of a negative number. That's not real numbers. That's complex number. Okay. All right. So we have the domain. So next, let's draw where do I draw my table? Okay, let me draw my table here. So we have okay, my domain is just 0 to infinity. That's my domain. And and then we plug in the critical points. So e to the minus 1 is here. So that separates the domain into 2 subintervals. Okay, and then we do f prime and f. For f prime, we plug in, where do we plug in? Here. Okay, so we know this can make it 0, and can you find a number in this region? Well, 1 is in there, right? 1 is in there, so we can plug in 1. Out of 1 is 0. 1 plus 1 is 2, so it's positive here. Okay, here, how do I find a number? I would say it's hard to actually know which number is in here, but you can think about a number that is close to 0. Okay, a number that is so close to 0 and is positive. Okay, and you know what's ln of x? So ln of x looks like that. When your x is getting close to 0, it actually goes to minus infinity. So ln of x is a very negative number, okay? And when you plus 1, it's still negative. And then, so we know that if f prime is negative, f is decreasing. If f prime is positive, then f is increasing. Well, decrease and increase, what do you call this guy? Yes, local minimum. So how do we answer it? F is increasing. You can also say f increases on e to the minus 1 to infinity. Okay? And f is decreasing on 0 to e to the minus 1. F has local minimum at x equals to e to the minus 1, and f has no local maximum. Okay? All right, that is example 4. So far, so good, everybody? All right. So let's continue in part B.